Have you ever shuffled your feet across a carpet on a dry day? Then when you reached for a metal doorknob, zap, you got a little shock. Or perhaps you've seen a balloon stick to a wall after rubbing it on your hair. These are common examples of something called static electricity. Static electricity is a fascinating phenomenon. It is all around us in everyday occurrences. It is different from the electricity that flows through wires to power our lights and appliances. That kind of electricity is called current electricity because it moves. Static electricity, as the name suggests, generally stays in one place. It's an accumulation of electric charge on the surface of an object, waiting for a chance to move. So what causes this static behavior? It all comes down to an imbalance of tiny little things called electric charges. Imagine these charges as very small particles. Normally, objects around us have a good balance of these charges. They are neutral, but sometimes this balance can be disturbed. Certain actions like rubbing two different materials together can cause these charges to move from one object to another. One object might end up with too many of one type of charge, and the other object with too few. This imbalance is what we call static electricity. To really understand static electricity, we need to zoom in, way in. We need to look at the basic building blocks of all matter atoms. Everything around you, from the air you breathe to the chair you're sitting on, is made of atoms. Atoms are incredibly small, far too tiny to see with the naked eye. Inside every atom there are three main types of these smaller particles. We have protons, neutrons, and electrons. Protons are said to have a positive electric charge. Electrons have a negative electric charge. Neutrons, as their name suggests, are neutral. They have no charge at all. Protons and neutrons are packed together tightly in the center of the atom, in a region called the nucleus. The electrons, on the other hand, are much lighter and whiz around the nucleus in specific regions. In a normal, undisturbed atom, the number of protons, positive charges, is equal to the number of electrons, negative charges. The total positive charge from the protons perfectly balances the total negative charge from the electrons. So the atom as a whole has no net charge. It is electrically neutral. This is the usual state for most matter. Everything is balanced and stable. Now that we know about positive and negative charges, we can explore how they interact with each other. There's a very simple, fundamental rule that governs their behavior. It states that like charges repel each other. This means if you have two objects that both have a net positive charge, they will try to push each other away. Similarly, if two objects both have a net negative charge, they will also push each other away. The other part of this fundamental rule is that opposite charges attract. A positively charged object and a negatively charged object will pull towards each other. There's a force of attraction between them. This attraction is a powerful force in nature. It's what helps hold atoms together as the positive nucleus attracts the negative electrons. It's also what makes a statically charged balloon stick to a neutral wall through a process called polarization, where charges in the wall rearrange. Imagine you take two identical balloons and rub both of them on a wool sweater. Now both balloons have an excess of electrons, meaning both are negatively charged. If you try to bring these two negatively charged balloons close to each other, you'll feel a force pushing them apart. This is the repulsion of like charges in action. Not all materials behave the same way when it comes to electric charges, particularly how easily charges can move through them. Some materials are very generous with their electrons, allowing them to move freely. These materials are called electrical conductors. In conductors, electrons, especially the outermost ones in their atoms, are not tightly bound to individual atoms. Instead, they can roam throughout the material, almost like a sea of electrons. This mobility of charges is what makes them good at conducting electricity. Metals are excellent examples of conductors. Copper, aluminum, silver, and gold are all very good conductors. This is why electrical wires, which need to carry moving charges, electric current, are typically made of copper or aluminum. If you apply a voltage or an electrical push to a conductor, these free electrons will readily move, creating an electric current. This flow of charge is what powers our devices. The ease with which charges move through conductors is a defining characteristic. On the other hand, some materials are very stingy with their electrons. The electrons in these materials are tightly bound to their atoms and cannot move around easily. These materials are called electrical insulators. So how do objects actually become charged? We've mentioned rubbing, but there are a few common methods. The most familiar is indeed charging by friction or triboelectric charging. This happens when two different materials are rubbed together. Due to differences in their atomic structures, one material might have a stronger affinity for electrons than the other. When they are rubbed, electrons can be physically scraped off one material and transferred to the other. The material that gains electrons becomes negatively charged. The material that loses electrons becomes positively charged. Consider the classic example of rubbing a glass rod with a piece of silk. Electrons tend to move from the glass to the silk. This leaves the glass rod with a deficiency of electrons, so it becomes positively charged. The silk, having gained these electrons, becomes negatively charged. Another method is charging by conduction, which simply means charging by contact. If you have an already charged object and you touch it to a neutral conductive object, some of the charge will transfer from the charged object to the neutral one. Finally, there's a more subtle method called charging by induction. This method allows you to charge an object without actually touching it with another charged object. We've established that electric charges exert forces on each other, likes repel, and opposites attract. But scientists want to know how strong this push or pull is. Does it change if the charges are bigger or farther apart? Charles-Augustin de Coulomb answered these questions. He used a torsion balance to measure electric forces precisely. By measuring the twist in a fiber, he quantified the force between charges. Coulomb's law is a powerful statement about the nature of the electric force between two charged objects. It tells us precisely how to calculate this force. The law highlights two crucial factors that determine the strength of this force. The first factor is the magnitude of the charges themselves. The force is directly proportional to the product of the two charges. This means if you have more charge on one object, or on both objects, the electric force between them will be stronger. Suppose you have two charged objects and we call their charges Q1 and Q2. If you double the amount of charge on Q1, while keeping Q2 and the distance the same, the force between them will also double. If you then also double the charge on Q2, the force will double again, meaning it becomes 4 times what it was originally. The second crucial factor in Coulomb's law is the distance between the centers of the two charged objects. The law states that the electric force is inversely proportional to the square of the distance between them. This is often called an inverse square law. What it means is that as the distance between the charges increases, the force between them decreases very rapidly. If the charges get closer, the force increases very rapidly. This square part is really important. Let's delve a bit deeper into that inverse square relationship with distance R2 in Coulomb's law. It has a profound effect on the electric force. If you have two charges a certain distance apart, they experience a certain force. Now, if you double that distance, so R becomes 2R, the new force will be 1 over 2R squared, which is 1 over 4R squared. This means the force becomes 1/4 of its original strength. It doesn't just get halved, it drops by a factor of 4. This rapid weakening of force with distance is a key characteristic of electric and gravitational forces. What if you triple the distance between the charges? If R becomes 3R, then the new force will be proportional to 1 over 3R squared, which is 1 over 9R squared. So the force drops to 1/9 of its original value. You can see a pattern here. A small increase in separation leads to a much larger decrease in the force. Conversely, if you decrease the distance, the force increases dramatically. If you halve the distance, making R become R over 2, the force becomes 1 over 2R squared equals 1 over 4 R squared equals 4 times stronger. This is why charges very close together can exert enormous forces on each other. Now let's think about the charges Q1 and Q2. The force is proportional to their product. Understanding static electricity and Coulomb's law is more than just explaining shocks or balloons sticking to walls. These principles are fundamental to our understanding of the physical world and technological applications. Coulomb's law describes forces responsible for the structure of matter. They govern how atoms bind to form molecules and interact to create substances. Without these forces, matter as we know it couldn't exist. Chemistry is about how electrons form chemical bonds. These bonds are electrical in nature. Molecular shapes, reactions, and properties are influenced by charged particles. Understanding electrostatics is key to chemical interactions and material properties. Electrostatics plays a crucial role in modern technologies. Many devices rely on static electricity. Photocopiers and laser printers use static charges to transfer images to paper. Industrial spray painting uses electrostatically charged paint droplets. Air purifiers use static electricity to trap particles.